Hello my friends, so today we are going to talk about dual vector fields or vector field interchange method. So what is a vector field? First of all I would like to explain about vector field and how a vector field works and what is a vector field actually. If you consider a plane and in that plane there are so many vectors pointing in different directions or maybe in the similar direction and all these vectors are of similar kind, so in these vectors, we can say that one thing is common, that is their kind are common, and therefore they form a vector field. Now, what is a vector field actually? Vector field is you can say the vector field is a combination or collection of similar type of vectors that do the same purpose, that serve the same purpose. Okay. So first of all, let us talk about planar vector fields. What are planar vector fields actually? Planar vector fields, we can say that these are kind of vector fields that lie in a plane or are independent of the third coordinate. I should say that if we are considering the Cartesian coordinate system. Okay, so since now we are not discussing about the Cartesian coordinate system, I am expecting it to be in the xy plane or some any other plane. We can just talk about some any other plane. Here we can say that a planar vector field is a type of vector field in which the other two components, okay, in which one of the component is 0 and the other two components are independent of the value of the former. That is, let us say if it's the z coordinate and it's 0, it will have absolutely no effect in the xy plane because they are just irrelatable, they are irrelatable. Okay, so first of all I would like to talk about and then I would like to talk about the solenoidal and irrotational vector fields. Now what are solenoidal and irrotational vector fields? Solenoidal fields are those kind of fields in which the divergence is zero. Okay, the divergence is zero, and if we write that in a differential format like the Gauss law, this is called the Laplacian operator, and if the Laplacian operator is done a dot product with the vector field, it will have some fx, fy, fz component or fr, theta, phi components, any sort of components it can have. And there is an irrotational field if the curl is zero. Now what is divergence? Actually many of us do not understand the meaning of divergence and we just learn the formulas, but divergence is the divergence of field vectors. That is, if some vectors originate at a point, we say that to be a uh, source or sink accordingly. If they are originating, this is called the source of divergence, and if they are terminating, we say that this is a sink of divergence. Here the divergence will be negative. In the case of a sink, the divergence will be negative, and in the case of a we can say source, the divergence will be positive, that is it will be greater than 0. And we are talking about the case in which the divergence is 0, it is actually 0. In that case we say that the field is solenoidal. And for irrotational, what is curl means when a vector just rotates around a point. When you vector field vectors just rotate around a point, they do not have any sinks or sources, they just curl. As the name suggests, they curl around the you can say the path. Okay, there are no sinks present here. Actually there is no sink here. And here we can say that magnetostatic vector fields are divergence free and rotation free in those regions of space where there are no electric currents. So what is the important condition for this to happen? It is that there should be no electric current, that there should be no electric currents in the region where we are actually seeing the field, that is in a local region actually I should say. The divergence should be 0 and the vector fields are called divergence free and rotation free if this condition gets satisfied. Okay, and same is in the case of electrostatic fields, but where there we talk about the charges, so that no other charges are present, they are also rotation free. Okay, and now let us talk about, so for both kind of vector field, that is for both electrostatic and magnetostatic, I have not written that, I must should have written that. So here we can understand that the vector fields, the electric field lines and the magnetic field line, they are all part of a vector field, and the equipotential lines form array of perpendicular curves. That means if I point the if I say that this is the field line, okay, these are two field lines actually. If I plot them, these are two field lines, and here we got two equipotential curves, two equipotential lines, and we know that they will be in the perpendicular direction because electric field points in the direction of decreasing potential. That is a very important point to be kept in our mind. and they cut each other orthogonally, that is perpendicular to each other. Now this is called the dual connection method or the equipotential curve method. Okay, so let us talk about it in a detailed manner. Here we can say the dual connection. What is the dual connection? This is the important part and the best part of this lecture, or the main crux of this lecture. What is the dual connection? The equipotential lines of one of the vector fields corresponds to the field lines of the other. This is called the dual connection. So if we are given any two fields, we have to just apply this rule to get the field lines of the other. If we know one of the field lines and the equipotential line, we can plot the others. Okay, so it can be asked that they will give you the potential function and they will ask you about each and everything, the dual field. Actually the you can say the corresponding field is called the dual field. Okay, so the name is generally the dual field. So here vector fields are not just defined by being divergence free and rotation free. That is not the single thing that defines a vector field. It should be divergence free and it should be rotation free. There are many other factors involved in this, but also by imposed boundary conditions. So here we have the imposed boundary conditions. Okay, so next what we should say, the electric vector fields have sinks, but magnetostatic vector fields do not have any such property. I already shown you that they just curl. They do not have any sink or sources. You can see here they are just curling about a point. This is the point, and about this point they are just forming a curl. And here they are originating or terminating. As I already discussed, it can be positive, negative, or zero. That is solenoidal and irrotational vector fields. So this is an example where we will discuss this example later. This is the main electric field, I should say the main field, and its conjugate field or the dual field or the corresponding field. The light diagram should be this is the main field and the corresponding field should be somewhat like this. I will discuss that later because this is a very important part of the lecture. Okay. First, let us consider this statement. What we are going to talk about right now is something that is completely out of GI syllabus, but we are not confined to that syllabus. Okay, so here we need to find the line flux. Okay, there are two types of flux. Actually, there is two-dimensional flux and three-dimensional flux. Two-dimensional flux, in that we talk about the electric field component perpendicular to a line, and in 3D we talk about the electric field component perpendicular to the area. So the both things are same, but in the 2D and 3D the length and the area parameters change. Okay, so here we should say the direction of electric field is in the direction of decreasing potential. We know that, and the curve intersect each other orthogonally. That means that this curve and this equipotential curve, this curve and this equipotential curve is cutting each other at 90 degree. And this V star, what is this V star? Nobody will get confused by V star, as it is the line flux, okay. And this V plus delta V is the equipotential curve, and this is the field line. Now we are going to find the potential and the flux relations in this shaded region, and that will do downwards. Okay, so here we should talk about two-dimensional and three-dimensional flux. In two-dimensional flux we take a reference line and a field line. Okay, now we see what amount of flux is passing between a point on this line and a point on this line. Since they never intersect each other, we will be able to find the flux between these region. So we'll say that dpl, that is planar or two-dimensional, can be calculated as e perpendicular into dl. And here I have shown a small diagram that this is dl and e is perpendicular to that sort of component we should have. And if we just integrate this, we will get 5pl is equal to e perpendicular into dl and p1 say p2. Okay, so here phi 3d, what is the value of phi 3d? That is e perpendicular dot dA and the to the closed integral of the surface area integral. Now here in the previous diagram, if I just redraw it, you can see that it is the same diagram. Flux between the reference line. Okay, so we are saying this as the reference line, and here we say V star R. V star R, that is the amount of flux, and it associates a scalar quantity. It associates a scalar quantity with each point of a field. Each point of a field. Okay, so let us talk more about that. You can say the green shaded region, the green shaded equation of V star R is, the green shaded region can be considered rectangular. Okay, so approximately the green shaded region can be considered as a rectangular region. This is the green shaded region and it can be considered a rectangular region actually. So we will using the geometrical interpretations and the mathematical interpretations too. So here V star R is constant, that's the relation actually we know that. And from the potential relations we know that delta V is minus delta minus mod of E delta L, and there decreasing potential, this is the sign that electric field decreases in the direction of increasing potential. So flux and field relation, that is delta V star is E perpendicular DL, that relation we have used here. And we just see that this is the sum, actually the sum is 0, the sum is 0, and this is a very symmetrical relation I should say. And it will be, it's obvious that will be the such sort of a symmetrical situation. So we relate the vector field er to its dual vector field E star r. So just like er we say there will be a dual vector field. Now what is a dual vector field? I already explained that a field in which the equipotential curves serve as the electric field lines and the electric field lines serve as the equipotential curves. Okay, from this relation we can say this is also true for E star r, this will be true for E star r too, because let us show the E star r field. So we can say now for the dual vector, change role for the vector field and scalar potential. I already told that. Now this will serve as the flux, this will serve as the flux, and this will serve as the potential function. So here we can see all the roles are interchanged. This is V plus delta V and V star. Okay, so the electric field will now pass like that, and this will be the flux, this will be the flux. As you can see, we will have this component perpendicular to delta L, actually to delta L will be perpendicular, and delta L star that will be parallel, and this will use for potential, V star will be used for potential. Okay, so let us take an example in which we say that VR is minus k ln r upon r naught. R is the radial distance. Now if I draw the equipotential curves, if I draw the equipotential curves, they are concentric circles. They are concentric circles. And if I find the electric field at a radial distance of r, I will be able to see that the electric field is k by r, and the flux that is equal to E times perpendicular. So this is a dl here this is dl, and dl can be written as r psi. Now here we just do that and k psi comes out, k psi comes out. That is, the flux is a function of the polar angle, the flux is a function of the polar angle. Okay, so let us talk more about that. So if I just find the dual field of that, I will know that the equipotential line, these are the equipotential lines. Now they will serve as the field lines, and the field lines, actually these are the field lines, now they will serve as the equipotential lines, we can already say. And the field lines are actually, you can say, the flux lines. More precisely I can say that they are the flux lines. Okay, and that would be better to say it as flux lines. Now here for the dual field we can say that E star R delta psi, E star R delta psi. Now what is E star? This is the dual field, and R delta psi must be the function for the potential. So R delta psi means some component like that. Here let us say this is R delta psi, and E will be somewhat perpendicular to that. So that will give us the potential function. That will give us the potential function, that is minus K delta psi, and E star is already minus K by R. We already know that. From this relation we can say that delta psi will get cancelled, delta psi will get cancelled, and here it will also get cancelled. So it will be E star R is equal to minus E star is equal to minus K by R. So here E star is equal to minus K by R. Okay, so how I got this K delta psi? That is from the function that we got above. Actually that is the this function. We already know that V star is equal to K delta psi, and since K is a constant, we will already say that this is delta V, and delta V means K delta psi, K delta psi. So if I just do that here, I'll get this relation, and since it is minus delta V, so I will get minus K delta psi. So minus K by R, and if K is mu naught I by 2 pi, we will get the dual field, that is the magnetic field. The constant determines that what field you choose. What field you choose. If I choose the magnetic field, the constant must be mu naught I by 2 pi. Now, what is the additional information we need here? The magnetic vector field along a straight current carrying wire is locally rotation free, but it is not necessarily conservative. That is, if the rotation free, that is if curl is 0, it is not necessary that it will be conservative, but it is always conservative for electric field. Okay, so we can also say that by seeing the v star, that is a multiple valued function, because the polar angle varies and the function varies, and that's why it is not always conservative, because the flux is not conservative. Okay, this is the analogous condition. This is the concentric circle system, and this is the field line system. Now here, what are equipotential curves? These dashed lines are equipotential curves. And what are equipotential curves here? These circles are the equipotential curves here. They just interchange their situations. Okay, so that proof can be proved by this relation, that vr is equal to, this is for the what to say, the wire. Actually, this situation is for this situation, that is the charged rod situation. And since we know that these will be the concentric circles from the above function, we already know that this will be the concentric circles. Here they will be the field lines. Here they will be the field lines. So I hope you enjoyed the video. This is quite a difficult concept. I think that you have to revisit the video once in a while. Thanks.